The irreversible threshold for surplus military aircraft is the smelting furnace. In 1946, at the War Assets Administration storage facility in Kingman, Arizona, thousands of combat airframes were routed for aluminum reclamation. The primary objective at this site was rapid material reduction. The procedural workflow was entirely destructive, designed to convert complex aluminum structures back into standardized industrial ingots. Boeing B-17D Flying Fortress, serial number 40-3097, was placed into this disposal queue. The stakes were absolute. This specific airframe represented the oldest surviving intact B-17 and the only remaining D model in existence. Once an airframe enters the reduction sequence, its structural and historical data is permanently erased. Accepted into the Army Air Corps inventory in 1941, this aircraft predates the mass production wartime variants. The early design parameters of the D model are distinct. It lacks the heavier defensive armament, later protective improvements, and enlarged tail surfaces that define the subsequent Flying Fortress fleets. The most prominent physical identifier is the early straight tail configuration, a structural geometry that was superseded in subsequent manufacturing blocks to improve stability. Its operational footprint was extensive. The aircraft flew combat missions in the Philippine theater immediately following the Pearl Harbor attack. The operational requirements during these early engagements demanded heavy payload capacity under minimal logistical support, pushing the unpressurized airframe to its design limits. As the Pacific theater evolved, the tactical utility of early model bombers diminished against advanced interceptors. Serial number 40-3097 underwent an operational pivot. It was pulled from the frontline combat roster and converted into a high-speed transport for Lieutenant General George Brett. This transition required removing weapons and unnecessary combat equipment, reconfiguring an offensive platform into a priority transport for senior command movement. The exact internal arrangement changed over time, but the aircraft's identity shifted away from a frontline bomber and toward a high-speed transport role. The aircraft served in this modified capacity until its retirement in December 1945. Its survival through the conflict was a direct result of this reassignment, keeping it out of the highest attrition zones while maintaining its mechanical viability. After retirement, the aircraft entered the War Assets Administration pipeline at Kingman, where airframes were drained, stripped of reusable assemblies, and cut down for metal recovery. Serial number 40-3097 sat in the staging area until Colonel Frank Kurtz, a pilot closely associated with the aircraft during its operational life, helped secure its removal from the disposal pathway and its preservation as a memorial asset. The airframe was spared intact but stripped of its active military designation. However, preserving a large, unpressurized aluminum structure requires active environmental management. A bomber is designed to withstand dynamic flight loads, but it is highly vulnerable to static atmospheric degradation. Without the constant maintenance cycles provided by active military service, an airframe left exposed to the elements begins to degrade. The intervention at Kingman secured the physical existence of the aircraft, but it placed it into a new logistical category. The challenge shifted from preventing immediate thermal destruction to managing slow atmospheric breakdown. After one final flight in 1953, the Swoose moved into outdoor storage at Andrews Air Force Base. The primary hazard was water intrusion. A bomber is assembled using thousands of mechanical fasteners, lap joints, and riveted seams. Because this specific variant was unpressurized, its fuselage was not built with the hermetic sealants required for high-altitude commercial or later military flight. It relied on aerodynamic tight fits and active drainage. Over decades of sitting stationary on an open tarmac, dirt and biological debris accumulated in the lower fuselage sections. The factory drain holes designed to clear internal condensation became completely obstructed. Rainwater flowed along the outer skin, entered the unsealed panel gaps, and pooled in the lowest structural cavities. This standing water initiates severe galvanic corrosion. The structural assemblies utilize dissimilar metals, where steel fasteners or brackets connect to aluminum skins and spar cords. When these dissimilar metals are continuously bridged by trapped moisture, an electrochemical reaction accelerates the loss of the aluminum material. The primary wing spar joints, which are the critical load-bearing structures of the entire aircraft, become highly vulnerable to this hidden degradation. The oxidation turns solid metal into brittle powder, permanently destroying the load paths required to keep the wing safely attached to the fuselage. The institutional trade-off for utilizing free outdoor space is the steady, irreversible loss of the primary artifact. Beyond electrochemical breakdown, the unprotected airframe faced mechanical damage from human interaction. Parked in an open, accessible area, the historic bomber became a target for unauthorized component removal. Vandalism and souvenir hunting systematically stripped the interior. Individuals removed flight instruments, control yokes, data plates, and accessible structural brackets. Each removed component not only erased a piece of historical data but also physically weakened the surrounding assemblies. A missing canopy panel or a torn-out side window immediately opened new, massive pathways for bulk water and debris to flood the flight deck and navigator compartments. The resulting damage was exponential, as the loss of one component accelerated the environmental attack on the adjacent systems. Even wind forces act destructively on a static airframe. Control surfaces like the elevators and ailerons are designed to be dynamically balanced in flight or mechanically locked on the ground. When hydraulic pressures bleed off completely and mechanical locks deteriorate, surface winds cause the control surfaces to continuously buffet and cycle. This unmanaged movement places cyclical stress on the hinges and attachment points, wearing through the dry bearings and tearing the aluminum mounts. By 1961, the accumulated damage forced the aircraft to be dismantled and transported to the Paul E. Garber Restoration Facility. The move did not solve the exposure problem, it changed its geometry. The aircraft remained outdoors, now with the wings and tail removed, leaving internal attachment bulkheads and main spar rings directly open to rain and humidity. For decades, the remaining bottleneck was institutional. Hangar space and funding were not immediately available for a massive, fragile object trapped in outdoor storage. Breaking that stalemate required an action beyond standard maintenance protocols. What institutional mechanism could finally move it indoors? The institutional mechanism arrived in 2007 when the National Air and Space Museum put the aircraft's future before a formal collections committee. The vote passed by a narrow margin of 5-4, converting the storage stalemate into a transfer decision governed by deaccessioning protocol, stewardship responsibilities, and the long-term interest of the museum, the public, and the object itself. The expected transfer of a restored combat veteran B-17G helped address the resulting interpretive gap, but the decision remained a formal collections management judgment. The National Museum of the United States Air Force agreed to eventually transfer a restored G-model aircraft known as Shoo 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 Baby to the Smithsonian. That exchange exposed the differing institutional priorities. The G-model represented the mass-manufactured wartime configuration and the European strategic bombardment story, helping satisfy the general public display requirement for a heavy bomber once moved, reassembled, and prepared for exhibition. The unique D model was a developmental link and a combat veteran of the earliest Pacific campaigns, but it required years of specialized stabilization. The military museum prioritized lineage and singularity, accepting the restoration burden, while the civilian museum gained a combat veteran B-17G for a different aviation narrative. Executing this level of institutional transfer is procedurally combative. The documentation required to deaccession an aircraft of this scale involves exhaustive condition reports, provenance verification, and legal indemnification. Every component, from the damaged wing spars to the remaining internal brackets, must be cataloged and transferred under a strict chain of custody. The receiving institution assumes total liability for the artifact from the moment the title transfers. This means the transportation risk, the restoration cost, and the long-term housing requirements immediately become the sole responsibility of the military museum. The civilian board effectively transferred a monumental logistical hazard to a new jurisdiction. The split reflected a deeper argument over the museum's charter. Some members favored retaining the unique airframe inside the primary national collection despite the lack of immediate restoration resources. The majority accepted the pragmatic conclusion that the weakened aircraft required specialized intervention elsewhere. In 2008, the transfer was finalized, turning the aircraft from a protected storage problem into a physical payload. The military museum had acquired the oldest flying fortress, but now had to extract it from the East Coast with decades of corrosion embedded in its load paths, fragile skin, and oxidized attachment points. How does a team move a massively degraded bomber across the country without shattering it? The fuselage, stripped of its main structural appendages, was mounted onto a custom flatbed trailer for overland transport to Dayton, Ohio. This method required precise routing to clear highway overpasses, navigate weight stations, and avoid tight radius turns. The fuselage was essentially an empty aluminum cylinder, structurally self-supporting along its longitudinal axis even when heavily degraded, and could withstand the continuous low-frequency vibrations of highway transit. The support cradles on the trailer were positioned at the strongest remaining bulkheads to prevent the airframe from sagging or twisting during the multi-day road trip. The wings presented a completely different structural profile. They are the primary load-bearing elements of the aircraft, originally housing the engine mounts, fuel cells, and main landing gear attachment points. Decades of outdoor exposure had severely oxidized the main spar roots. Bumping or flexing these structures beyond their degraded tolerance would induce catastrophic cracking along the spar caps. Road transport was rejected. The wings needed an airlift to avoid continuous bending moments over rough pavement. The initial operational plan assigned a C-5 Galaxy to execute the airlift from Andrews Air Force Base. The C-5 is designed specifically for massive, awkward cargo profiles. It features a lifting nose visor and aft doors that allow for straight-in, horizontal loading. This configuration eliminates steep ramp angles, which is critical when handling fragile, rigid structures that cannot bend to accommodate a sharp transition. During the staging sequence, the C-5 experienced a mechanical failure. The jet's nose visor malfunctioned, as did the aft cargo doors, leaving no option for upload and grounding the primary lift platform. The mission was immediately transferred to an available C-17 Globemaster III. This shift introduced a severe geometric penalty. Unlike the straight-in loading path planned for the C-5, the C-17 forced the truck, trailer, and wing load up an angled aft ramp, where floor height, deck clearance, and the breakover point could impose sharp loads on a corroded aluminum wing. The danger was not speed, it was uncontrolled geometry. To safely upload the wings, the 89th Aerial Port Squadron altered the approach geometry with a custom ramp extension built from heavy wood shoring. By stacking and securing dimensional timber, the loadmasters lengthened the ramp, decreased the incline, softened the breakover point, and distributed the transition load. The upload sequence was executed at a continuous crawl, with clearance between the delicate wing roots, loading winches, and aircraft deck monitored inch by inch. Once inside the cargo hold, the wings were secured to the deck using specialized tie-downs, tensioned to hold the structures during turbulence without inducing compressive stress on the fragile spars. The C-17 successfully delivered the structures to the restoration facility. The high-risk physical extraction was complete. Safely inside the new hangar, what configuration does the museum target for a hybrid airframe? Restoring a historical aircraft forced a binary choice: return it to a factory baseline or preserve the modified command transport that survived the war. A factory reset would remove non-standard repairs, mission-specific alterations, and operational scars. Conservation would protect the evidence acquired in service. For this airframe, the two outcomes were mutually exclusive. The identity of this specific airframe is defined entirely by its deviations from the factory baseline. In 1942, while operating in Australia, the aircraft sustained severe structural damage. The repair sequence bypassed standard logistical supply chains. Maintenance crews grafted the complete tail section of another damaged B-17D directly onto the primary fuselage. This field-modified, hybrid configuration inspired its operational name, combining the halves of different birds to create a functional whole. Replacing this specific tail section with a newly fabricated standardized D model assembly would erase the exact physical proof of its wartime survival. The historical anchor is the grafted metal itself. The modifications extended far beyond the external structure. Inside the aircraft, the evidence of that transport phase remained physical rather than interpretive. Operational bomb racks, ammunition tracks, and defensive gun mounts had been removed. Passenger seating, heavy cargo tie-downs, and improvised bulkheads marked the aircraft's second wartime function. A pristine bomber interior would therefore misrepresent the surviving aircraft. turning the display toward reconstruction rather than artifact conservation. Faced with this evidence, the museum administration issued a definitive configuration mandate. The final target would be the end-of-war transport configuration, with the grafted tail and interior changes retained as primary historical evidence. This institutional decision creates a severe operational constraint for the engineering teams. A traditional restoration allows technicians to manufacture new structural components, rivet fresh aluminum panels, and apply modern finishes to make the repair visually uniform. A combined restoration and conservation approach narrows those options. The team must retain original skins, markings, and field evidence wherever feasible, while repairing or replacing material only where structural integrity and exhibit safety require it. The Australian tail section is not meant to disappear into a seamless factory finish. Its mismatched geometry, field repairs, and non-standard rivet patterns remain part of the evidence the museum is trying to preserve. The configuration mandate now controlled the engineering work. The artifact had to support its own weight for long-term public display without turning its visible evidence into a blank factory finish. Standard aviation overhauls can reskin wing sections and conceal structural splices under modern finishes. Here, load-bearing safety had to be achieved beneath the original aluminum skin. To execute this mandate, the restoration technicians must first map the hidden deterioration. The airframe is inspected and documented to separate surface oxidation from damage that threatens structural integrity. Critical areas such as spar joints, wing roots, and main load-bearing bulkheads receive the closest scrutiny. Where internal members are too compromised to support the aircraft safely, technicians repair, stabilize, or fabricate replacement structure as needed, while protecting as much original material as possible. Where new internal components are required, they are shaped to restore the load paths needed to attach the massive wing structures to the central fuselage. Protective treatments and isolation barriers reduce future corrosion between old and new material, keeping the repair focused on static display loads rather than cosmetic uniformity. Once the internal structure is secured, the outer surfaces are treated under the conservation goal: clean, stabilize, and protect the surviving 1940s paint, original stenciling, and bare metal patina without erasing the aircraft's service history. Operational dents, visible field repairs, and other surviving surface evidence are documented and preserved when they can safely remain. The objective is to halt active degradation while keeping the aircraft in the visual context of its final mission state. This rivet-by-rivet process requires a massive, sustained labor allocation. Following a deliberate institutional pause to allow the facility to complete the stabilization of another historic heavy bomber, active work on serial number 403097 officially resumed in 2023. The engineering team is currently executing this combined restoration and conservation plan simultaneously across the fuselage, the grafted tail section, and the isolated wing assemblies. The scale of this minimally invasive workflow imposes a severe timeline constraint. The meticulous nature of hiding necessary structural repairs beneath historic skins reduces the speed of assembly to a crawl, and the project is estimated to require at least 7 years to reach completion. Upon completion, the National Museum of the United States Air Force will place the aircraft on permanent public exhibition as the only surviving straight-tail early model aircraft of its type, preserved in its final command transport configuration.